Okay, so we are into 6C, and we're looking at momentum and collisions. And so this is the part of the chapter where things run into each other and bounce off or stick together. And we look at those sorts of interactions of materials and talk about how they move. So when Newton was figuring out the laws of motion, this is actually one of the first concepts he dealt with. He was looking at how big an object is and how fast it is moving, and he called the multiplication of its mass and its speed the quantity of motion. That was the initial term. So the bigger something is, or the faster it's moving, the more movementness there is, right? The more there is an energy of motion going on. And so he called this the quantity of motion. Later physicists named this term momentum. And so we use momentum now, and there will be lots of examples of momentum in a moment, but we use that term in common language, and you should be fairly familiar with what that term means. It has to do, again, with the mass of an object and the speed of the object. So if Janine wanted to move something by running into it, if there were like a really big, I don't know, let's say a really big bean bag, a big bean bag, and Janine wanted to move it, Janine would get a running start and jump into the bean bag, and it would slide a little bit because Janine would carry a certain amount of mass and a certain amount of speed, right? If Nico wanted to move the same beanbag, Nico could get the beanbag to move without running quite as fast because Nico is more massive than Janine, right? And so I'm not picking on either of you, I'm just identifying, right? So, and Caleb would have to run at an in-between speed, between Janine, right? Which is why football players tend to be huge people, especially the linemen, tend to be big because they may not be fast, but they have mass, and they are harder to move, right?
They may not have mass, but
Five people.
No, that would be you. You may not have mass, but you're fast. The linebacker might not be fast. Okay, so speed and size are what matters. So if you look at these two things, this is a Lotus, Lotus Esprit race car, and Lotuses are not very heavy at all. As a matter of fact, a Lotus Esprit tricked out for racing like that can be picked up by 3, at the most 4 people. Could just stand around the thing and pick it up. They're pretty light. This, however, this is a super dump truck. One of my fraternity brothers was raised in Wyoming in a coal mining community, and he drove one in high school. That was his high school job. Imagine some of you in high school don't even have a driver's license to drive a VW Bug. My friend in high school got a license to drive something the size of, well, much bigger than my house. So these are significantly heavy pieces of equipment. The momentum between the two is very different. This one carries almost all its momentum in its speed. When you get hit by a Lotus Esprit, the damage to your car is because of how fast the thing was moving, not because it's so heavy. If you got hit by the super dump truck, the damage to your car would be because of how massive it is, not necessarily because of how fast it's going. These things top out at like 12 miles an hour, but they're massive. So yeah.
if it hits your car, it'll probably just go right under.
Right over. Yeah, right over. Yeah. So this is
That's a person.
a full-grown man.
Dang.
So
Or go like under this thing.
yeah.
That could be like the size of our house.
Which is why it's a very different thing to get hit by an airsoft pellet than it would be to be hit by a cannon shell from a battleship.
There's no difference at all.
Good then.
No, very different experience.
You die.
You get hit by this, you go, oh.
Ouch.
You get hit by this, you go, dead. You don't even get a chance to react. You're just, oh, now I'm in heaven or hell. Hello, Jesus. And that's why we shoot these massive steel things out of a battleship cannon, is because it makes a lot more difference. Can you imagine a battleship going to war and they start spraying the enemy with airsoft pellets?
Ow.
You know, and the guys are like, really? Why'd you show up? So yeah, there's that. So momentum, the formula for momentum is mass in kilograms times velocity in meters per second. And the shorthand for momentum. It's not actually P, it's the Greek lowercase rho, but it looks like a P, so go ahead and write P. But it's actually the Greek lowercase r. So rho equals m times v, but you can use p, that's fine. Momentum, mass times velocity. So the unit is given by the equation. It's just kilogram meters per second. We don't name that anything, you know. Like kilograms times meters per second squared is a Newton, but kilograms times meters per second is just kilogram meters per second. If you were to divide a momentum term by a time term, you could get a Newton out of it. But right now, we just have kilogram meters per second. Okay, no proper named unit term. Okay, so picture. Let's look at this this falcon and talk about his momentum. So, what is the momentum of a 750-gram peregrine falcon in a dive at 109 meters per second? It's incredibly fast. Think about how long a second is. And a peregrine falcon in full tuck dive like that covers 109 meters, longer than a football field, like 1 1/4 football fields every second. It's screaming fast, okay? And the way these birds hunt is they will be way above a duck or some other bird that they want to eat. And they'll get into one of these full tuck dives and come straight on the bird, and then they don't catch the bird. They simply flick their talons out at the last second and rake the bird with their claws. The bird is dead. It just got hit by 6 razor-sharp talons at 100 meters per second. And then the peregrine will flap out its wings and stop its dive and then catch the bird that it just killed and bring it to its nest. It's awesome to watch.
Video.
Unless you're the duck, then it's not so awesome. But let's look at this. So 750 grams, we have to convert that to kilograms because the formula is kilograms. So 750 grams is 0.75 kilograms, and the velocity is 109 meters per second downward. Okay, so rho equals mass times velocity. Put the numbers in, 0.75 kilograms times 109 meters per second. You multiply that together and you get 81.75 kilogram meters per second. And we have 2 significant digits from our 750 grams, okay? So I go to 2 significant digits and I say 82 kilogram meters per second. That's the quantity of motion with which that peregrine falcon ran into the duck. And then we're going to say, what is the momentum of a 3.4 kilogram sooty albatross, which is the largest flying bird in the world? Largest bird that can fly. Yes, is the sooty albatross. What is the momentum of a 3.4 kilogram? That's about an 8-pound bird, okay? Flying at 3.55 meters per second. So a lot bigger bird, a lot smaller momentum, a lot smaller speed. Mass is 3.4 kilograms, and the velocity is 3.55 meters per second. We're going to say he's flying east, just to give him direction. Rho equals mv, so 3.4 kilograms times 3.55 meters per second is 12.07 kilogram meters per second, with 2 sig figs, 12 kilogram meters per second. So here I have a big, slow-moving bird and a light, fast-moving bird. And you can see that the light, fast-moving bird, in this particular example, has more momentum than the big, slow-moving bird. Okay, so size is not the only thing, it's size and speed. Okay, so the falcon's mass is only about 1/5 of that of the albatross, but the maximum speed carries it almost 7 times the momentum. So there you go. You'd rather be hit by an albatross than hit by a falcon. Kind of a cool thing while you're writing that down. The Air Force, when they were working with how to fly faster and faster and faster, ran into a problem with jet engines, where the jet engine developed so much turbulence at the intake that at a certain speed it couldn't work anymore. The air wouldn't flow into the jet engine. The air would flow around the jet engine, and the jet go to a certain speed and the engines would essentially fail. And they were trying to figure out how do you solve that problem, and they actually solved the problem by studying the shape of the nostril on the peregrine falcon. And because God knew better than Air Force engineers. And the shape of the nostril allows intake at very, very, very high speeds without turbulence. And so the air goes into the bird's nose, and they actually used that same shape to engineer the intakes on high-speed fighter jets. So it's kind of cool. It's a neat example of God's design being used by physicists. So you already know, we're at Roman numeral 2 now, you already know that energy as a whole is neither created nor destroyed, but changes form. The same is true about momentum. So when objects collide, the net momentum of the system is conserved. So if, again, we were talking about Janine running into a beanbag versus Nico running into a beanbag. When Janine runs into the beanbag, Janine carries with her a certain amount of momentum. And the beanbag also has momentum. It just has zero momentum because its mass times its zero velocity, its value for momentum is zero. But then when Janine runs into the beanbag and sticks to the beanbag, right? Because not sticks to it, but like runs into it and lands on the beanbag, right? Then her mass plus the beanbag's mass is the new mass of the system. And you can calculate the speed of the beanbag based on the mass before collision, the mass after collision, the net momentum that Janine brought to it, and then the momentum that's left over. So momentum is conserved the same way that other kinds of energy are conserved. If Nico and Janine were to run into each other, like playing football, and Janine were to tackle Nico.
Yeah!
Okay?
Go, Nico!
Now, the system of Janine at her mass at a high velocity, we're going to just assume that Janine can outrun Nico, that she can. Nico is running at one speed. Janine is running at a faster speed, and Janine tackles Nico. The new system, when Janine locks up Nico and they go to the ground, the new system of Nico's mass plus Janine's mass will move at a certain speed that you could calculate if you had the two speeds before, right? It's all conserved. It all equals out before and after the collision. So let's look at an example of that.
Oh, yeah.
Longest bowling strike ever. Recorded video. So when the bowling ball got to the pins, there was momentum in the bowling ball, and the momentum of all the pins was zero, because whatever their mass is, they're sitting still. So anything times zero is zero. But then when the bowling ball hits, all the pins scatter. And if you were to very carefully analyze the momentum of all of the pins, they would add up to the same quantity as the momentum of the bowling ball, because the momentum of the bowling ball then got conserved and spread out amongst the motion of all the pins. So before and after a collision, the momentum is conserved. Okay? So formulas, yay math, yay math. We get to analyze collisions. And when you look at this, you have two objects, or you could have more, but we're going to say you have two. You have object 1 and object 2. And you have object 1 before the collision, and you have object 1 after the collision. That's what this little prime or not or apostrophe or whatever you want it to be is, right? This is object 1 after the collision. This is object 1 before the collision. This is object 2 before the collision. This is object 2 after the collision. So the little apostrophe, when you read it, you say prime. And that just means another example of this thing, right? So M1V1 plus M2V2 equals M1V1 prime plus M2V2 prime. And so what you're saying here is the mass times the velocity of the first object and the mass times the velocity of the second object before they collide. The sum of that is the same as the sum of object 1's momentum and object 2's momentum after they collide, right? And you could have lots of objects here. In this example, I just have 2. But you could, in theory, have 6 things that run into each other, right? A bad car accident on the freeway could have 10 things that run into each other. And so a shorthand way of saying this is sigma mass volume equals sigma mass volume prime. And what that means is the sum. Have you guys ever seen sigma standing as the sum of things before? Have you gotten to that part of math yet? You will soon if you haven't. Sigma very frequently in math means the sum of, add up everything, okay? So the sum of all the masses times volumes, masses times velocities, equals the sum of all the masses times velocities, okay? So before and after the collision, those will equal each other. Momentum of object, I just said this, didn't I? Momentum of object 1 before the impact, momentum of object 2 after the impact. So I already said this. There you go. Okay. Sum of the momentum of all objects before the collision, sum of the momentum of all objects after the collision. So there are 2 kinds of collisions. There are collisions where things ricochet, and there are collisions where things stick. Okay, so if you were to, let's see. If you have an object here, okay, a little mass, and the object runs into, the little mass runs into my mouse. It bounced off just a little bit. Well, that time it missed. But it runs into the mouse and bounces off just a little bit. That's called an elastic collision. The things ricochet off of each other. And when my little mass ran into my mouse, the mouse moved just a little bit. And most of the movement happened in this, because my little mass, while it had all the momentum, it only had a little bit of mass. And the mouse weighs a lot more. So we have 2 things that run into each other and bounce off, and you can analyze the collision and the ricochet, and you can determine the momentums of the objects before and after the collision. Inelastic, where it would be a significant amount of energy is changed into another form other than kinetic energy, and the objects tend to stick together. So this would be like playing football, where 2 football players run into each other and stick together. The one guy tackles the other one and locks them up, and they fall to the ground. And in that case, the kinetic energy of the 2 people became other forms of energy. It became sound, it became heat, it became deformation of the pads, it became all kinds of other things, but it's no longer kinetic energy. It got lost to friction, and the 2 things don't bounce off of each other, they stick together and fall to the ground. So elastic collisions, they ricochet. Inelastic collisions, they stick. In the demo we're going to do on Friday, we're going to kick a soccer ball at a pumpkin, and the soccer ball will bounce off the pumpkin, and the soccer ball will both move. And then we'll shoot an arrow at the pumpkin, and the arrow will not bounce off the pumpkin. The arrow will go into the pumpkin. And so you have an example of an elastic collision and an inelastic collision. Okay. There are, of course, there are collisions in between. There are semi-elastic collisions, but whatever. The thing you need to remember is that no matter what happens to the objects, whether they bounce off or stick, momentum is always conserved. Okay. Kinetic energy may change into other forms of energy, but you could still find all of the momentum after the collision that you found before the collision. Okay. Momentum is always conserved. Well, I thought I had more pictures. I guess, no, I do. There you go. So these 2 guys, when they run into each other, are going to bounce off. Their horns don't, interlock, and they get stuck to each other. So these 2 guys are about to have a headache, and their collision is elastic. They will bounce off of each other. Here, when you play billiards, which is what this guy is playing, the balls bounce off of each other. Those are elastic collisions, and you can analyze the momentum before and after the balls come in contact with each other. Okay. This is another elastic collision, the bat and the ball. If the ball were to stick to the bat, that would be pretty fun. And so they bounce off of each other, and you can analyze the momentum before and after and see that the momentum is conserved. Okay. Here, this is an inelastic collision. Blue dude and orange dude now stick to each other and go to the ground. And their momentum is still conserved, but their kinetic energy has been lost. The energy has been transferred into other forms of energy. Okay. I have more. Yes, it is.
Oh.
This very unfortunate circumstance was an inelastic collision. The car hit the tree, and the kinetic energy went into changing the shape of the car. And that's why the car is no longer drivable, because the kinetic energy of the car became another form. It became the energy that it took to deform that metal. The momentum was still conserved, though. You could find that momentum afterwards, but unfortunately, the energy is no longer kinetic. It's other things. And this is a very famous kind of demonstration where somebody lays on a bed of nails and puts another bed of nails on top of them with a cinder block on it and has somebody crush the cinder block. And everybody is always amazed because they're like, oh my gosh, the person is going to get totally destroyed by the nails. But no, because the cinder block is brittle, the energy of the hammer strike goes into changing the shape of the cinder block. And very, very, very little energy, if any, goes into the nails and into the person. The energy goes poof on the cinder block. Now, if you were to just lightly sit on the cinder block, now the guy's in trouble, because the cinder block is then absorbing that energy slowly and transferring your weight to the guy who's going to get squished. But if you go fast, you almost don't even feel it. So it's a very famous demonstration because the energy changes form and doesn't remain kinetic energy.
Would you do it right now if you had the supplies?
Yeah, I mean, I'm confident enough in the physics of it, yes. You just have to trust that the other guy's not going to go slow, and he whales it quickly. So we started talking about, please find the video. Please find the video. Oh, sad. Oh, no, we've got another one. That's right, the video's. So the peregrine falcon, with a momentum of 82 kilogram meters per second, dives on and attacks a city albatross, which we already discovered has a momentum of 12 kilogram meters per second, and rides it to the ground, which is not what they actually do. They rake it and then come back and pick it up. But we're going to pretend that it rides it to the ground, where it begins to eat it. What is the speed of the new peregrine albatross complex as it goes downward? So the peregrine has a momentum of 82, and the albatross has a momentum of 12. Now, to analyze this properly, you would need trigonometry, which you don't have, so we're going to simplify it just a little bit. We're just going to pretend that they're going the same direction for a moment, okay? So the sum of the mass times the velocity beforehand equals the sum of the mass times the velocity afterwards. So the peregrine is 82, and the albatross is 12. We know that. We've already solved that. So when you add them together, the peregrine is it weighs 0.75 kilograms. The city albatross weighs 3.4 kilograms. We're going to add them together because now it's one thing. The peregrine grabbed it and rides the other bird to the ground. 3.4 plus 0.75 times an unknown velocity. We don't know the new velocity. So 104 kilogram meters per second equals 4.15. There you go, kilograms times the unknown velocity. Divide by 4.15. So the new pile of bird goes to the ground at 25.06 meters per second. We have to correct for sig figs. 25 meters per second. So the one bird was doing 109. The other bird was doing, what was the other bird doing? Something small. Anyway, small, flying along. Here comes the peregrine. We're going to pretend that the other bird dove to try to get out of it just so that we don't have to do trigonometry. The new bird hits it at 109 miles an hour and catches it, and they don't go to the ground at 109 meters per second. They go to the ground slower than this bird was going, but much faster than this bird was going because the momentum is conserved. They go to the ground as one unit. Okay? So mass times velocity before equals mass times velocity after. The falcon was streaking toward the earth at 109 meters per second until it struck the albatross. then its downward velocity greatly decreased because of its increased mass. The albatross wound up falling at twice the speed it was originally flying because of its impact with the falcon. Okay, so momentum is conserved either way. And now the video. This is